Hello and welcome to this lecture about stresses in beams under bending. However, before we can start discussing the topic of this lecture, we first have to discuss the coordinate system. Adopting a consistent coordinate system is an important step, since because of it some minus signs may or may not appear in your equations later on. So let's start by looking how we define the coordinate system in this course. As a use case, let's start with this general beam, which can have any cross-section, but is drawn here with a rectangular cross-section. As in all courses so far, we will use a right-handed coordinate system. For this course, we define y as positive downwards, which may seem strange, since in aerospace we often work with lift, which is positive upwards, but since the weight will always act downwards, we still opt for this option, also because it nicely fits in the other approaches. Z will be along the length of the beam, which means that using the fact that we have a right-handed coordinate system, we find that x is positive pointing out of the screen. This may be slightly different than what we have used so far, but it is the one we will use consistently in this class and also in follow-up classes when talking about beam bending. Now that we have a coordinate system, we can look at what this means for other parts of the problem statement. And for this, let's start with what we define as a positive load. In general, an external load takes the sign of the resultant in the coordinate system. So, a positive external load, in means of point loads, means that if the load is acting downward in the positive y direction, we regard it as positive. A distributed load is also positive when it is acting downward. For the moment, it is a bit more tricky since there is no clear axis along which the moment is working. However, when using the right-hand rule, your thumb is moving in the positive x direction, hence pointing out of the screen. This will lead to a positive moment. Hence, you get a counterclockwise moment being defined as positive. So on this beam, all forces and moment applied are considered to be positive. The next question is, what does this mean for the deformation? When do we consider deformation to be positive? Actually, we can be relatively brief about this aspect. The displacements and slopes are positive according to the established coordinate system. Hence, a displacement downward, as depicted here, is considered to be a positive displacement. The slope is positive if it increases the rate of the deformation in the positive direction. Hence, an angle that is clockwise is defined as a positive slope. Next part to discuss is what we consider as a positive internal loading. This is important to consider since in many equations it is the internal load that we consider and not the applied loads directly. Of course, the internal loads are linked to the applied loads, but it is important to consider what is a positive internal load separately as well. For the definition of an internal load, we have to think back of the definition of a positive stress that we saw in the first week. And for this we used this three-dimensional cube. And we said that the stress was positive if the direction of the stress and the outward normal were both in the positive or negative direction. The same holds for the internal loads. They are positive when the coordinate sign of the outward surface normal matches the coordinate sign of the resultant load. In other words, when they are both positive or both negative. The internal load is considered to be positive. Let's, for example, look at the internal load on the right-hand side of the infinitesimal element highlighted on the figure. The outward normal on this side is pointing in the positive z direction. Hence, a positive internal force is when it points in the positive direction. Hence, an internal force downwards is considered positive. For the moment, you need a positive moment, hence a counterclockwise moment is considered positive on this side. For the opposite side, we see that the surface normal is pointing in the negative z direction. Hence, an internal load will be positive when it's acting in the negative y direction. Hence, an internal vertical load is positive on this side when it's acting upward. And for the moment, you need a moment that is around the negative x-axis, since the outward normal is in negative direction. Hence, a clockwise moment is considered as a positive internal moment, because a negative times a negative gives you a positive. Now, you may be slightly concerned when you have already read up in the book about this part, because if you look at the coordinate system, the positive loading and positive internal load definitions, you will see they are actually different from the textbook. Now, we do not do this to confuse you, but we have chosen this coordinate system since it's also used in follow-up courses, so we want to be consistent throughout the curriculum. And we also want to make sure that you are familiar with a consistent coordinate system, because the book is not completely consistent. Let's look at that coordinate system and definitions of internal load to explain what I mean with that. In the book, the length direction of the beam is denoted by x. Y is positive upward, and to obtain a right-handed coordinate system, z is pointing out of the screen. This is a different choice than we make, but no problem with consistency yet. When we look at the positive external load, we see that the point loads acting upwards and the distributed load pointing upwards are positive, since the positive y direction is upward. And the moments are positive when they are counterclockwise around the positive z-axis, which is still pointing out of the screen. In terms of deformation, it is now positive when it is upwards. So this is the other way around of what we had, because the y-axis is pointing upwards rather than downwards. So far, everything is still consistent. However, for the internal loading, they use exactly the same definition as we used as well, while the y-axis is pointing in a different direction. And this is where the problems occur, since this definition of the internal loading system is not compatible with the coordinate system. If we look, for example, at the shear force on the right-hand side of the infinitesimal element, we see that the outward normal is pointing in the positive x direction, and thus we would expect that a positive internal force acts in the direction of the positive y-axis. But this is not the case. It works in the negative direction of the y-axis, hence they have introduced an additional negative sign, which we will come back to in a later video. We decided not to teach you this coordinate system, but rather a consistent coordinate system. Probably you are wondering now, why does this matter? It is just an additional negative sign that appears, and you can easily fix this on the fly when deriving the formulas. And you are correct, at least for easy problems. If you look at what we do in this course, we do scalar mathematics. We multiply a number a with a number b. And when we think about the problem, we can imagine how a structure will deform, and thus know whether it should be in tension or compression, and that way correct for the sign we expect. The problem appears when you want to apply these same principles to more complex problems, because in the end, this course is just your first step into structural analysis and design. And later on you may have to write a piece of code to calculate the stresses or displacements. Hence you cannot just think about the problem and make the required changes. You will be using vector mathematics. And there the cross product gives a different result whether you do A cross B or B cross A. The difference is just a minus sign, but you do not want to trace this back for every calculation. And you do not have to if you use a consistent sign convention. Else you will have to debug your code by checking in each line whether it has to be a plus or a minus, and it will cost you a lot of valuable time. So just to wrap it up, this figure shows you the coordinate system and the sign convention we will use during this course for a positive internal load. It is a consistent system where the positive deflection and positive internal loading are consistent with the chosen coordinate system, something that will make your life a lot easier later on.